Dear participants, dear colleagues and friends, good evening and welcome. Welcome to the online Scientific Turkey public lecture series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize with the aim of sharing the passion for science and research, the power and wonder of science with a wide audience, as well as fostering scientific curiosity and science culture in the society. It is my sincere pleasure to welcome all of you for this special event. Those of you joining us through the Zoom platform and those of you watching us through all social media platforms of TÜBİTAK, the Scientific and Technological Research Council of Turkey. It is also my distinct pleasure to introduce you our tonight's very special speaker, Dr. Phiala Shanahan from MIT. She's going to give a great talk, From Quarks to Nuclei, the building blocks of the universe. Phiala Shanahan is an assistant professor at the Department of Physics of MIT. Professor Shanahan's research interests are focused around theoretical nuclear and particle physics to understand the structure and interactions of hadrons and nuclei from the fundamental quarks and gluon degrees of freedom encoded in the standard model of particle physics. In particular, using for these analytic tools and high-performance supercomputing. To overcome computational limitations in QCD calculations for hadrons, and in particular for nuclei, Professor Shanahan is pursuing an innovative program to integrate modern machine learning techniques in computational nuclear physics studies. Professor Phiala Shanahan grew up in Adelaide, Australia, and obtained both her Bachelor of Science and PhD degrees from the University of Adelaide in 2012 and 2015, respectively. Before joining to MIT Physics faculty in July 2018, Professor Shanahan was a postdoctoral associate at MIT from 2015 to 17 and held a joint position and assistant professor at the College of William and Mary and senior staff scientist at the Thomas Jefferson National Accelerator Facilities from 2017 to 18. Professor Shanahan is a recipient of a number of awards and fellowships. In particular, she is the recipient of National Science Foundation Career Award and Department of Energy Early Career Award and the American Physical Society's 2021 Maria Coppert Mayer Award, which recognizes outstanding achievement by early career woman physicists. With this, I want to thank once again Professor Phiala Shanahan for joining us and look forward to her talk. Phiala?
Thank you very much. It is absolutely a delight to be here, albeit virtually in Turkey, and to have the opportunity to speak a little bit about our modern understanding of the structure of matter made up from the protons, neutrons, and atomic nuclei in our universe. So matter is, of course, composed of atoms, which have densely packed nuclear cores of protons and neutrons bound together, orbited by a cloud of electrons. And our modern understanding is that the structure of matter, in fact, goes one layer deeper, and that the protons and neutrons inside the atomic nucleus themselves have a substructure. They're made of matter particles, called quarks, held bound or glued tightly together by the strong nuclear force, manifesting as force-carrying particles, known very aptly as gluons. And to the best of our current understanding, the quarks and gluons are fundamental particles. That's it. They can't be divided any further, and this is as deep as the structure of matter goes. The quarks and the gluons and their interactions are encoded in what's known as the standard model of elementary particles. So this framework, which you see here on this slide, was put together in the 1970s And it includes just 17 fundamental particles here and describes 3 of the 4 fundamental forces. So you see here the matter particles called quarks, which come in different types or flavors. We have particles like the electron and its neutrino and heavier cousins. The gauge bosons here, we already met the gluon just before, which are the force carriers for the strong and weak nuclear forces and for the electromagnetic force. And of course, the Higgs boson, which you might remember was the last piece of this puzzle to be found experimentally in 2012 at the Large Hadron Collider, 4 decades after it had been predicted from this theory. So the Standard Model describes electricity and magnetism, so that's forces between charged particles. It describes the strong nuclear force, which we'll see a lot more about today, which binds the quarks together into protons and neutrons and binds the protons and neutrons together into nuclei. The weak nuclear force, which is responsible for example, radioactive beta decay, but it does not include gravity, which is described by the separate theory of general relativity. And being able to unify the Standard Model with gravity is one of the big open questions that we face in physics today. So the equations describing this theory, so the interactions of all of those particles we saw in the previous slides, are beautifully symmetric and elegant. And the theory, which, as I said, was developed in the early 1970s, has explained and precisely predicted an incredibly wide variety of experiments and phenomena. So that's really to say the Standard Model has become a well-tested physics theory, arguably the best theory of the structure of the matter in our universe that we've ever had. And to give you just one example of the overwhelming success of this theory. So the magnetic moment of the electron, that's how much torque an electron feels in a magnetic field. This is the most accurately verified prediction in the history of physics. So what I'm showing here on this slide is actually the anomalous magnetic moment or the deviation in this quantity from the classical result. And you can see here the comparison between theory and experiment with a theory calculation up to 12 significant figures that took 30 years of effort. And if there are any physics graduate students here in the audience, you can put that effort in perspective when I say that calculation is up to 5 loops. That's 12,000 Feynman diagrams. And from all of that effort, what we see is a beautiful consistency between theory and experiment here. And so to the best of our understanding, aside from this sort of simple static quantity, the Standard Model also describes many more complicated aspects of the structure of matter at all scales. So from the structure of the proton at the most fundamental level, how the quarks and gluons come together to form the dynamical structure of a single proton, in principle, all the way up to the structure of the elements built from protons and neutrons, which you'll recognize here in the periodic table, to nuclear reactions at a cosmic scale. For example, those inside the sun, or those inside reactors for energy generation, for medicine, and all the way through to the dynamics inside neutron stars, which are the most dense known objects in the universe other than black holes. Now, of course, despite its incredible successes, we also know very clearly that the Standard Model does not describe everything we observe about the universe. And we make massive efforts as a physics community to understand and constrain physics beyond the Standard Model. So for just one example, the Standard Model can't explain dark energy. That's the name we give to whatever is responsible for the accelerating expansion of the universe. And as well as dark energy, which you can see takes up this very large fraction of the energy density pie of the universe, we actually know that most of the matter in the universe is not described by the Standard Model at all, but is in fact the mysterious stuff that we call dark matter. And we'll talk more about dark matter later, but essentially it's non-Standard Model matter that we know is there because we see it interact gravitationally, even though we don't know a lot about its properties. And so the Standard Model only describes this tiny 5% sliver of the energy density in the universe. And that's not all. Of course, gravity doesn't fit into the Standard Model, and there are other hints. The fundamental particles we call neutrinos, which are massless in the Standard Model, actually have masses in nature. There's an asymmetry between the amount of matter and antimatter that we see in the universe that we can't explain if we start from the Big Bang and allow only Standard Model interactions. And there are questions we can ask about the naturalness of the various parameters in our theory. And so then, of course, one of our primary missions in physics is to understand in what ways our best current theory of nature falls short in describing all of the things we observe about our universe. And so just one way in which we look for so-called new physics is what we call the intensity frontier. So that's when we have experiments with the sensitivity to probe absolutely the rarest Standard Model interaction. And if we're looking for such very rare events, well, we build very large detectors to increase our statistics and increase our probability of making an observation. So these types of experiments are typically built with the matter that we can assemble en masse here on Earth. That's nuclei. So then to constrain the new physics that we're searching for, we need to understand the physics of the nuclei in our detectors first. So one example of these types of experiments that we'll come back to is dark matter direct detection experiments here on Earth, looking to directly see the interaction of dark matter with nuclei in our detectors. And another example, you can see the cartoon picture on this slide, is from the deep underground neutrino experiment, which is an experiment currently being constructed in the United States to learn more about the properties of the neutrinos and understand their mass hierarchy and mixing properties better. Okay, so then this idea of studying the theory of the standard model. This is interesting both for its own sake, that's as an exploration of the structure in our universe and to see whether we can really see the emergence of all of the complexities of nuclear physics up to a cosmic scale coming out of this fundamental theory. But it's also important to constrain the backgrounds and benchmarks for many searches for physics beyond the standard model, in which we, of course, use standard model particles in our detectors. So these two themes roughly outline the talk today. And at the end, I'll circle back and talk about how new advances in algorithms in computing feed back in and enable us to go further in our study of the standard model and hence the structure of the matter in our universe. Okay, so to talk about first principle standard model calculations is to talk about the strong force. That's quantum chromodynamics. And so this is the force responsible for binding the quarks and gluons into protons and neutrons, for binding the protons and neutrons into nuclei, and for forming other types of exotic matter like the quark and gluon plasma. So this force is, of course, relevant to questions like the structure of a proton and the structure and interactions of nuclei, which we said that we'd like to understand from the standard model. Now, this theory is unfortunately challenging to study, especially at low energy scales, like those relevant to the structure of a nucleus at rest in a detector in your experiment. So at those low energy scales, the coupling scale of the theory becomes large. So what I'm showing here on the figure, on the horizontal axis is the energy scale, and on the vertical axis is the coupling of the theory. And as we move to the left on this plot, the coupling becomes large. And what that means is that we can't expand in powers of the coupling. If the coupling was small, like it is over here at large energy scales, then a perturbative expansion works. The second power, when you square the coupling, is smaller than the first power. The third power is smaller again, and so on. And you can expand to some order and stop for an answer at some precision. When the coupling is small, we can't do that. And so at the low energy scales, what we're left with is a computational approach. So the only known way to study the strong interactions at low energy scales in a systematically improvable way is through what's called lattice field theory or lattice QCD, where the idea is that the equations of QCD, remember our theory of quantum chromodynamics that describes the strong interactions, which look like integrals over the values of the quark and gluon fields, they become discretized onto a four-dimensional space-time grid in such a way that they can be done numerically. So you want to imagine calculations within this lattice QCD framework as being very high dimensional integrals in essence, in something like 10 to the 9 to 10 to the 12 variables in state-of-the-art calculations. So doing calculations in this theory is really a massive computational challenge. The challenge is really so large that even with the most powerful supercomputers in the world and with significant resource investments, so I know the numbers in the United States where something like 10% of open science supercomputing is devoted purely to these sorts of calculations every year. Even with that sort of a massive resource investment, we're still computationally limited. There are many problems that we know how to solve, especially when it comes to questions of understanding nuclear physics from the dynamics of the underlying quarks and gluons, that we know how to solve, that we simply can't with current computing. And so I'll come back to this as motivation for some new algorithms later in the talk. And just to give you a sense of scale, so that some of the calculations I'll show results for would take something like 10 to 20,000 years on a very good desktop computer. So that's roughly the scale that we're talking. But as we'll see, we can in fact do such calculations, and there's a deep complementarity between theory and experimental investigations of the structure of matter in our universe. So let's talk a little about what we can learn about the structure of matter from first principle standard model calculations. As a first example, we know, of course, that the neutron is ever so slightly heavier than the proton. And this simple fact is absolutely essential for life as we know it. If the proton was heavier than the neutron, then it wouldn't be stable. And so then the proton, which are the nuclei of hydrogen atoms, would decay. The sun couldn't have survived for more than about a century after it was formed. Without electrostatic forces to support them, solid bodies would collapse rapidly into neutron stars or black holes. No atoms would ever have formed, and we wouldn't be here to know. So this very small mass difference is absolutely essential. And as we see, it comes from a delicate balance of the strong and electromagnetic interactions. So we can measure the mass difference between the proton and neutron experimentally. And you can see that the orange line on this figure. So here the vertical axis is the proton-neutron mass difference, and the orange line is the experimental result. What we can do with theory calculations is understand this mass difference. So it's been really within the last 5 or 6 years that we've been able to show directly from the standard model how that very small but very important mass difference comes as the delicate balance of the strong force pushing it one way and the electromagnetic interactions pushing it the other way, which you can see here on this chart, to give us a cancellation where the theory calculation agrees beautifully with the experimental result. So we have a first example of the complementarity of theory and experiment in understanding what we observe about our universe. We can measure this experimentally, but from theory, we can really understand where it comes from at a most fundamental level. Now, I only have a time to give you a small taste here, but first principles calculations can also reveal aspects of proton structure that we can't measure experimentally. And so here, let's take an intuitive example. Here's a cartoon of the pressure distribution inside the proton. Now, the proton is stable, right? The quarks are confined inside the proton. So if you imagine a pressure distribution, if there's any sort of an expanding force, it has to be countered by a compressing force for stability. So what's shown in this plot is the pressure distribution as we move out from the center of the proton in a radial direction. So on the horizontal axis here, we have that radial distance out from the center of the proton. And on the vertical axis, you have the pressure distribution multiplied by that radial distance squared. So I'm showing this quantity because this is what needs to integrate to 0 for stability of the proton. Okay, so if we have a peak, that's a repulsive pressure, it needs to be countered by a trough, a confining pressure for stability. So this is a nice cartoon. Looking at this cartoon, we can ask some very straightforward questions. Well, what's the peak pressure in the proton? Is it more like a bike tire? That's something like 10 to the 5 Pascal? More like the bottom of the ocean, that's 10 to the 8 Pascal? Or is it closer to a neutron star? That's 10 to the 34 Pascal, roughly. What about the radial extent of the pressure distribution? Is it similar or different to what we usually think of as the radius of the proton, which is the proton's extent as experienced by an electromagnetic probe, so the charge radius? What about the radius of its pressure distribution? Is that the same? And finally, how do the different fundamental particles, the quarks and gluons, contribute to this? Do they contribute in similar ways or in very different ways to build the pressure distribution of the proton? So recently, we've been able to actually calculate the individual quark and gluon pieces of the proton's pressure distribution for the first time to begin to answer these sorts of questions. So this is another nice example of the complementarity between theory and experiment. So the quark contribution to the proton's pressure distribution was measured experimentally, but the gluon parts had never been determined before our recent theory calculation. And then what we can do by combining theory with experiment, we can put them together and have a first complete determination of the pressure in the proton. And what we find is actually that the pressure inside the proton is greater than what's estimated for the interior of a neutron star, the densest known object in the universe other than a black hole. And also that the quark and gluon contributions are somewhat different. You see here, this is now actual data, no longer a cartoon. You see separately in green, the quark contribution, and in pink, the gluon contribution, and in blue, the total. And we see the green and pink curves are quite different. The gluon contributions here in pink significantly extend the radial size of the pressure distribution. And so this is an example where by combining theory and experiment, we have a complete picture of an aspect of proton structure for the very first time. Okay, so turning now from the very, very small, the dynamics inside a single proton, to the cosmic scale. As I said earlier, our understanding is that the Sabre theory of elementary particles describes the primordial nuclear reactions through which the universe evolved. So immediately after the Big Bang, the world was a hot and dense particle soup. And then as the universe expanded and as it cooled, matter formed, galaxy formed. And so immediately after the Big Bang, the universe was filled with neutrons, protons, electrons, positrons, photons, and neutrinos. And from there, then all of the elements were created by a chain reaction called Big Bang nucleosynthesis. So this chain reaction that I'm showing here on this slide happened in roughly the first 10 seconds to 20 minutes after the Big Bang. And you can see in this illustration is the start of the process through which heavier and heavier elements were formed. So the very, very start of this chain reaction, this part here, this is what's called the radiative capture process, where a neutron and a proton combine to form deuteron, so a two-body nucleus, and emitting a photon here. So here's another picture of this reaction. So recently we've been able to show that we can understand this very first nuclear reaction that occurred in the universe from the Standard Model. So from the very same theory through which we understand the complicated internal dynamics of the proton. So this was both the first nuclear reaction in the universe and the first calculation of a nuclear reaction from the Standard Model using this approach. And so what we see is that we can indeed compute from the Standard Model, and in particular from the strong interactions, nuclear reactions. So calculations of this process was one of the first times that we were able to show that photonuclear reactions, so that's the interaction of a photon with a nucleus, are different from the photons coupling to the individual protons and neutrons. So we can call that difference a two-body contribution, different from the photon coupling individually the protons and neutrons inside a nucleus. And what I'm showing here on this slide are this key two-body contribution to this process. The yellow star is the relevant value in nature from experiment, and the points here and the bands show theory calculations extrapolated to the physical point. So the reason there's an extrapolation is that because of computational costs, the calculations are done using values of the quark masses, so the fundamental particles in theory, that are heavier than those in nature, and then extrapolated down, which is a more computationally efficient way to reach this point. So in this case, there's an experimental result to compare against and see that we understand our theory calculations. But in many other cases, we don't have experiments, or experiments are difficult and have large uncertainties. And then again, in those cases, we see that the combination of theory with experiment really gives us new insights into the universe. So another example of an important nuclear reaction that we've recently calculated from fundamental theory for the first time is one involved in the chain reaction that powers the sun. So stars like the sun, they emit light through the conversion of hydrogen here to helium in a nuclear chain reaction that you can see here on the slide. So the photons emitted here at this point in the chain reaction, they work their way out to become sunlight. So if we look at just this first step in the proton-proton fusion chain reaction, that's in fact the proton-proton fusion process, which again, we've recently calculated for the first time from our fundamental theory. And even more recently, we've calculated a different process, tritium beta decay. So this free-body decay process here, which is a different process, actually the simplest example of a nuclear decay through the weak interactions. And in fact, these two processes, although they look a little different, can be used to constrain the same fundamental two-body part of these interactions. So the difference of these interactions from the interactions of just a single proton or neutron at a time. And so that's what I'm showing here on this slide. You can see the green constraints on this quantity from experiment or from phenomenology are actually less precise than the theory calculations we've managed over the last few years. And so better constraints on this quantity are important, not just to understand the processes that I mentioned before, like the proton-proton fusion process, but are relevant for understanding future neutrino detectors, and they'll compete with a new muon capture experiment. So we can use calculations of one quantity to inform experiments of others. And so the upshot here, what I really want to convey is that we're in a real precision era for these sorts of standard model calculations for the properties of a single proton. But for nuclear physics, we're in the very, very beginning of a new era of understanding, where we're making very first controlled calculations of nuclear physics from the fundamental particles. And we're at the very edge of being able to really link nuclear physics to the standard model in this robust and controlled way through theory calculations. So over the next decades, there's great potential to push this further. So to connect from the standard model to some of the fundamental questions about the emergence of nuclear complexity. And in particular, to interface between these sorts of first principles QCD calculations that I've been discussing with some of the approaches used to explore questions about fine tunings and naturalness in nuclear physics. So fine tunings that we observe that are deeply important for our existence, like the production of carbon in our universe through what's called the triple alpha process, which I'm showing on this slide, for which it's really important that a particular state of carbon, so the Hoyle state, an excitation of carbon, is very close to the energy of beryllium here plus the alpha particle. And so being able to see these sorts of fundamental properties that we observe in nuclear physics come out of the standard model. Okay, so to reiterate, just to sort of wrap up this section, we're really at the very beginnings of something exciting here, of connecting standard model calculations to nuclear physics in a robust, systematically controlled way through calculations that we're only now beginning to have the technology to do, the computing to do. And over the next decade, we'll really see this come into its full potential. So as well as understanding the structure of matter for its own sake, I said that standard model calculations can give us critical information for searches for new physics. So let's look at an example here. For just one example, let's come back to one of the biggest questions of our age. That's the question, what is dark matter? Now, dark matter, it's really very mysterious. We've never seen it directly in a detector, but we know that it's there. We've deduced its existence from overwhelming evidence that there's something beyond our understanding of the standard model, and the best theory that fits what we observe is dark matter. The story of dark matter goes back quite a long way. So by about 1980, it was already widely recognized that we have a major problem in our understanding of the universe. So what we observe, looking out at the stars, the planets, the galaxies, it doesn't match what we understand. So this picture shows the Coma cluster. That's a large cluster of galaxies that we can see from Earth. And from this particular cluster, it was noted since about 1930 that something doesn't quite add up. The gravitational attraction needed to hold the cluster together is more than can possibly be generated by the luminous matter that we see. It's like something else is acting gravitationally to hold the cluster together, something that's acting like matter gravitationally, but it's dark. And we see similar things in many other ways. For example, in the rotation curves of galaxies. So here we have a galaxy, and what we're showing is how fast everything's rotating as we move out from the center of the galaxy here, from the center along this axis, we're moving out along the radial direction. The red curve shows what we expect from visible matter and from standard Newtonian gravity. The white curve shows what's actually measured using starlight or the Doppler shift in the 21 centimeter hydrogen line. And what we see from the data is that everything seems to be moving too fast. Unless there's something acting gravitationally, the galaxy shouldn't be held together at all, but as it rotates, it should be flinging apart into space. And just one last example, here we see the famous bullet cluster. This was discovered in 1998. And it's an example when we were really able to see clusters of galaxies collide. So in blue, this is false color, of course. We see the location of the matter that we can infer is there through gravitational interactions, by how light from other galaxies is bent around matter through what's called gravitational lensing. And in pink, we can see the visible matter. That's what we can see is there through light, through X-rays. The separation between the blue and the pink here, that can be ruled out as a statistical fluke to better than about 1 part in 10 to the 15. And we can understand this separation within the picture of dark matter. If we start with galaxies, with matter and dark matter, and as they collide, the dark matter just sails right on through and the dark matter collides and stays stuck in the center, then we can understand exactly this picture that we see. So what is dark matter and how does it interact? Well, we know that it doesn't interact through electromagnetism. It's dark. And it doesn't interact through the strong force, since cosmic rays, which are made of protons, don't interact with it. It does certainly interact through gravity. That's how we know it's there. And if it only interacts gravitationally, then it's a good chance we'll never detect it or make it in any conceivable particle accelerator. But maybe, just maybe, it might interact with the standard model weakly, that's through the weak interactions, and then we have a chance of detecting it in experiments here on Earth. Okay. So although we don't know what dark matter is, then we do know what it's not. So it's certainly not stars and planets because it's dark. It's not dark clouds of normal matter. It doesn't absorb radiation. It's not antimatter. Otherwise, we'd see unique gamma rays that are produced when antimatter annihilates with matter. It's not galactic mass black holes because of how many gravitational lenses we see, although I should say they're in some corners of some of these parameter spaces are not entirely ruled out. But we do have a lot of theories for what dark matter could be, from theories with extra dimensions or supersymmetries to new particles like dark photons, sterile neutrinos, extra Higgs particles. And so from all of these different possibilities, all of these different theories, we would have dark matter with different predicted properties. So here are just a few shown in a chart, which shows the particle mass on the horizontal axis against on the vertical axis, how strongly the particles would interact with normal matter. So then to learn more about what dark matter is and to rule out some of these possibilities, what we want to do is put constraints here on this space. If we can see that particles of a certain mass here couldn't interact more strongly than this with the proton, then we can place a line, a cut in this space and rule out all of the theories of dark matter on one side of the cut. So there are many ways to try to place constraints in this space, but one way is to search for so-called WIMPs. Those are weakly interacting massive particles in detectors here on Earth. So the broad idea is to build a detector deep underground and to wait for dark matter to hit the nuclei in the detector. And so these sorts of experiments can either see dark matter, or if not, they can put constraints on how strongly dark matter interacts with the nuclei in the detector for it not to have been seen, and rule out possible models of dark matter to leave only those that are consistent with the fact that we haven't yet seen dark matter in the detector. So for example, putting constraints on this space looks like this. So this plot looks quite complicated, but it's essentially the same figure that we saw before. So on the horizontal axis, we have the mass of our dark matter particle. And on the vertical axis, we have how strongly the dark matter particle interacts with normal matter in the detector. The lines on the figure show the results from different experiments, and none of them have detected dark matter. So to interpret this, all of the space above the lines is ruled out. So one thing I want to point out is that translating from what is seen, or rather what's not seen, that's dark matter interacting with the nuclei in the detector, to this figure, which constrains the strength of the interaction with the proton, is implicitly making a translation from the nucleus to the proton that relies on a theory understanding of the structure of the nuclei used in the detector. So for example, this line here for the xenon experiment, the nuclei used in that detector are xenon, which is a very large nucleus with 130, 140 protons and neutrons. And there's been an implicit translation from not seeing dark matter hit xenon to placing a limit on how strongly dark matter interacts with a single proton or neutron. So that's what we see here. As I said, in fact, these constraints assume that what happens is that dark matter interacts with only a single proton or neutron in a nucleus at a time. And so it's of course possible that dark matter might interact with multiple protons or neutrons in a nucleus at a time. And through first principle calculations, very similar to those that I discussed are revealing aspects of proton structure, we've recently found that this assumption may not be as good as was first thought. So here, what I'm showing in this figure is the fractional nuclear effect in the relevant quantities describing spin-independent dark matter interactions with nuclei. So those quantities are called the scalar matrix elements. Although we don't know the microscopic theory of the weakly interacting massive particles, we do know that the low energy limit of a generic spin-independent interaction is what's called scalar. And so the scalar matrix elements are the relevant quantities here. So this figure is showing the deviation from the assumption that dark matter interacts with a single proton or neutron in a nucleus at a time. So we have different types of interactions in the different colored blocks here, and we have different nuclei here in the different panels. So the deuteron, the diproton, and helium-3. And what you see is that in particular for helium-3, on the very right-hand side of this plot, we see effects as large as 10%, which work to decrease the strength of the constraints from dark matter direct detection experiments. So while there are still some significant systematic uncertainties in these calculations that need to be controlled, so in particular, most experiments use much larger nuclei than helium-3, which was the largest nucleus that we studied. What this is a strong warning that unexpectedly large multi-body effects really can't be neglected in the interpretation of dark matter direct detection experiments. That is, in that translation step of going from not seeing dark matter hit xenon to what we infer about the strength of interactions of dark matter with protons and neutrons. And so theory really still has an important role to play in this arena of interpreting the results of our experimental searches for dark matter. So again, we see this synergy between theory and experiment. So as I already mentioned, I showed results for calculations of helium-3, but the nuclei actually used in these dark matter direct detection experiments are much larger. For example, xenon is common in some of the major experiments, and that has atomic number 131, which is much larger than atomic number 3 for helium-3. So why not study these nuclei directly? The answer is computational cost. And in fact, we have compounding factorial and exponential growths in cost as we go to larger nuclei. And so at the moment, with current technology, with current computer hardware, calculations are only now becoming possible with controlled systematic uncertainties for light nuclei with atomic number less than about 5. And so there are many, many reasons that we might be interested in larger nuclei. So on this theme of new physics, not just for the dark matter connection, but for many others of the intensity frontier experiments that I mentioned before. So I mentioned before the deep underground neutrino experiment that uses an argon target, so that has atomic number A = 40, for example. So there are a few ways to get from small nuclei to larger nuclei. The first is to interface and to couple, as I mentioned earlier in the talk, with ab initio many-body methods, where the protons and neutrons, instead of the quarks and gluons, are the fundamental degrees of freedom, using tools like what's called nuclear effective field theory. And simultaneously, we can work to extend the capabilities of our lattice QCD calculations through new algorithms. Which brings me to the last short segment of this talk, which is how can novel algorithms based on artificial intelligence and machine learning open new possibilities in this field? So when we're talking about using artificial intelligence for theoretical physics calculations in particular, one thing is absolutely critical. We are doing well-defined, precisely defined, mathematically defined theory computations. Direct calculations from our precisely spelled out theory. So to maintain the rigor of the approach, we must preserve exactness in all of our AI approaches. So developing and using provably exact AI is absolutely key as we think about AI for first principles theoretical physics calculations. So let me give you an example of a computational problem in first principles theory that we're addressing with provably exact AI. So one of the challenges in lattice QCD calculations is the sampling problem. So in doing our very high dimensional integrals numerically, we need to generate a set or ensemble of field configurations that describe the background quark and gluon dynamics of the standard model. So these configurations actually have a complicated Lie group structure, but as a cartoon, you can just think of them as much larger versions of the images like the ones I'm showing here, where we want to sample these sorts of images with a precisely known probability distribution. Configurations like these ones, which have correlations at some characteristic scale, as you see here, are very likely, and configurations like this one, which is just random noise, are very unlikely, and we want to generate a specific distribution of these samples. The way these are traditionally generated is through what's called Hamiltonian or hybrid Monte Carlo, which you can think of as being a coupled walk in position and momentum space through Hamiltonian dynamics to explore this space of configurations. And it is much more efficient than a random walk in such a high dimensional space. What this practically means is that we're generating samples in a chain by updating from one to the next to the next. And there's some correlation between the samples in the chain, described by an autocorrelation time. And that time is related to the cost to generate independent samples, which might require some number of updates to decorrelate. And a particular challenge is that because this algorithm is close to local, or you can also think of it as diffusive, what that means is that the update physics on some fixed physical scale of interest, like the size of the proton, you need more and more updates to decorrelate your samples as the lattice spacing gets finer and finer. So this is a manifestation of critical slowing down in this context. It's a huge computational problem, especially for nuclear physics calculations. And this is a challenge that we aim to beat with AI tools. So this problem, this sampling problem of generating these field configurations, of course, has immediate parallels with the image generation problem that's received a lot of attention in the machine learning community over the last years. So if we can design an AI algorithm that generates pictures like this, so these are not photographs of people, these are fake AI generated images of faces, and you can go to this website here, thispersondoesnotexist.com, and every time you refresh, you'll have a new fake generated picture of a face. So if we can design an AI algorithm to generate pictures like this and not this, then surely we can use a same sort of algorithm to generate configurations like this, which have very specific types of correlation structures and not configurations like this. So this is an underlying motivation. And we see that although there's a very, very clear analogy between these two problems, there are also very clear differences. And the first of those differences is apparent already from this slide. In this case, if we want to generate images of faces, we never want this picture. This is just random noise. It doesn't look like a face at all. We never want that. In our case, this configuration might be very unlikely, but we do in fact want it to occur with a very precise probability given by the underlying quark and gluon dynamics of our theory. So if we stack up a benchmark image set for machine learning versus a set of field configurations for a lattice field theory calculation, we can see the similarities and differences. So the first is the one that we already mentioned. If you're generating pictures of people, it's really each image that has meaning. You want each image to look like a picture of a person. In our case, it's only the set of samples with a very precise probability distribution that has meaning. There's also differences in other ways. So we have what we call an extreme inverted data hierarchy. So if we look at this benchmark image set for machine learning, each image is described by something like 3,000 numbers, and there are 60,000 samples available for training. In our case, this hierarchy of numbers is inverted in an extreme way. So like I said, there's something like 10 to the 9 to 10 to the 12 degrees of freedom per sample in our lattice field theory case, and we only need order thousands of samples. And so any approach that uses a set of training data to train the AI algorithm won't work in our case. And then there are other differences. In an image, local structures are very important. An eye or a nose has its own local structure in a picture of a face. For us, it's really the long distance correlations that define the physics. In images, you don't have a lot of symmetries, maybe a translation invariance inside the frame. In our case, we have complex physics symmetries, things like gauge invariance, so symmetries of internal degrees of freedom, translation invariance, but with periodic boundary conditions. And so it becomes very clear that out of the box AI tools won't be appropriate for these sorts of theoretical physics calculations. And we need custom AI for physics from the ground up with all of these guarantees of symmetries and exactness built in. So constructing these sorts of custom architectures for physics is actually one of the foci of our brand new institute. This is our logo, the Institute for Artificial Intelligence and Fundamental Interactions that we just launched this year in the Boston area, which focuses on exactly these sorts of questions of what we call ab initio AI, building physics embedded deeply into machine learning and artificial intelligence approaches. So in the interest of time, I'll give you just one very broad idea of one approach to this generation problem using AI via what are known as flow models. Now, the idea behind flow models is very simply just a change of variables. If you have a map that takes you from an easy to sample distribution to the distribution you're actually interested in, And moreover, if that map is invertible with a tractable Jacobian, then you're done. You just take samples from the easy distribution, you put them into your function, and out come samples from the distribution that you want. And the invertibility and the tractable Jacobian means that even if this map isn't quite exact, you can correct for the errors using a known algorithm, so a Metropolis Hastings accept reject step. We can build this sort of a map while maintaining all of the features we need by constructing a complicated function as the composition of many simple layers with specific features. And we can even develop those layers to bake in exactly the symmetries of our theory, which is a lot easier said than done. But then the learning part of the machine learning here is the optimization of all of the free parameters of this function to give us the closest approximation of this map, if you like, a trivializing map between the easy and the hard distributions. And so then using our optimized function, we have an approach that we can make mathematically and provably exact. And as I mentioned, to do this, we really have to go back to the drawing board. But we've in fact developed architectures with all of the properties and symmetries we need for lattice field theory built in. And I'm going to avoid going into detail here, but here's an artist's impression of what coupling layers in our sort of custom architectures look like. And I'll also show you an example of the effect. So this figure shows the cost of generating field theory samples using conventional approaches here in orange and in gray, and then using the algorithm we developed here in blue for a toy model. And you can see that the cost of the conventional sampling approaches here diverges exponentially badly as we move along the horizontal axis here towards topological freezing in this theory. So tuning the parameters of the theory towards critical slowing down, while sampling from the AI algorithm remains fairly flat in cost, and it's out here at the parameters on this side, orders of magnitude more efficient than conventional sampling approaches. So this is really a proof of principle success. As I said, it's in a toy model, and we need to do a lot of work to scale it up to impact the sorts of first principles physics calculations I've been talking about. But the idea I want to leave you with here is just that this is the very beginning of this sort of ab initio AI, where we're building in fundamental physics principles into AI architectures. But it's already clear that there's huge potential for these sorts of tools in this context of understanding the structure of matter from first principles theory calculations. And so let me just finish with a reminder of the story that we've seen. So first principles calculations of the strong interactions in the standard model are revealing proton structure and revealing nuclear structure in new ways. So from basic details of the proton's internal dynamics that we're understanding for the first time by combining theory and experiment, like the example of the pressure distribution, to our very first principles calculations of simple nuclear reactions, like those governing the burning of the sun or the first step in Big Bang nuclear synthesis, through to critical theory input for searches for new physics beyond the standard model. And then as we continue to push the physics frontier, a new generation of provably exact physics-informed machine learning algorithms is promising to enable calculations that were previously computationally intractable. And it's already clear that with all of these developments over the next decade or so, it'll be a really exciting time as we continue this quest to understand the universe from the most fundamental building blocks that we know. Thank you very much.
Thank you very much for this very exciting and comprehensive talk. Now we can...
My pleasure. I'm very happy to take any questions.
Thank you very much. So now we can pass to question answer session. Where questions, please ask questions, write in a message using chat button of the Zoom platform, or you can directly using microphone ask the questions. Please, questions. So we have one message.
I'm not sure if I can see the chat. Perhaps you could read it out.
Not from me, but under my name, it is coming from YouTube part of the seminar. Not I am asking, but some people under my name, because I am host here, that's why. Can you read this?
Perhaps you could read it out. I'm not sure I can see the chat while sharing my screen.
Yeah. First of all, thank you very much for your valuable information. What is the phenomenon called the Fermi motion? And can you briefly explain? Could you give information about eta meson, electroproduction? Is electroproduction an elastic scattering process? Indeed, 2 or 3 questions.
Okay, so we can start with the question about Fermi motion. So Fermi motion is the name we give to essentially the motion of nucleons bound inside a nucleus. So there's a few things to unpack in even the statement that I just made of nucleons bound inside a nucleus. So we know, in fact, that a nucleus is not really protons and neutrons stuck together, but that it's composed of quarks and gluons from the standard model, like everything we showed. But we find that the protons and neutrons themselves are actually fairly good degrees of freedom at that scale. And what that means is that if you think of a nucleus, even though we know that actually everything is made of quarks and gluons, if you think of a nucleus in terms of protons and neutrons stuck together, you have a very good picture of its structure. And so then the Fermi motion is in this picture of a nucleus as being protons and neutrons stuck together. Those protons and neutrons move. And that comes out of exactly what we've been discussing at the most fundamental level, the fact that what we have is a dynamical soup of quarks and gluons being created and destroyed, quark-antiquark pairs appearing and annihilating again through the bubbling of the quantum vacuum. And that what become associated into proton and neutron degrees of freedom fluctuates over time through these quantum dynamics. And so essentially you can understand this Fermi motion if you go all the way back to the quark and gluon degrees of freedom of the standard model. But it is that motion of the proton and neutron degrees of freedom.
Thank you. We have another question from Toprak Koç. I wonder, do you people try to implement those AL algorithms into the quantum computing technology? They are way more faster than TPU-based computers. Quantum computers are already proved their performance, and I think your algorithms will work faster than the quantum computers.
Yeah, so quantum computing is very exciting. And of course, there's massive amounts of work also in my field, also by one of my graduate students, to design quantum algorithms for these sorts of problems. Now, the thing is that right now, quantum computers aren't at a scale to be competitive with the scale of the calculations we're doing on classical computers. So remember that I'm saying that we're really pushing the limits of classical computing using the most powerful supercomputers in the world. And while there have been significant advances in quantum computing, you would need thousands of tightly entangled qubits where you can maintain that entanglement over long periods of time in order to be able to approach the sort of scale that we're doing classically. So essentially, my answer is that your intuition on this is spot on, that if we can first formulate exactly how to put this theory efficiently onto quantum computers, then design quantum algorithms in order to do the calculations of interest, we could really open up new perspectives in this field. But we're basically still back at the formulation step and not yet up to the scaling up to the same scale as classical calculation step of that process. So maybe in the next few decades, we'll see some really exciting changes on that front.
Yes, thank you. More question, please. So if no more questions, perhaps, Phiala, we can stop here. We were extremely happy to have you with us. Thank you so much once again. What do you think?
My pleasure. Sure. Thank you very much. This was delightful.
So, bye.
Bye-bye.